Next, let's explain the concept of the friction circle. This is a top-down view of a tire. During cornering, the tire is subjected to a longitudinal force, Fx, and a lateral force, Fy. The resultant force of these two is F. The limit of F depends on the maximum friction the tire can provide, which is calculated as mu times W. Here, mu is the coefficient of friction between the tire and the load, and W is the vertical load on the tire. We can visualize this limit as a circle surrounding the tire. The radius of this circle is mu W. This is what we call the friction circle. If W decreases, meaning the vertical load on the tire drops, the circle shrinks. Consequently, the maximum total force F decreases, reducing the valuable force for both longitudinal and lateral grip. To help you better understand the friction circle, let's watch some real-world footage. This is onboard footage of Honda Civic Type R at the Nürburgring. Pay attention to the 4 circles displayed in the center of the screen. These represent the friction circles for each of the 4 tires. As the vehicle brakes, load transfers from the rear axle to the front axle. Clearly, the front tire's friction circles expand, while the rear ones shrink. If we maintain the demand for braking force on the rear tires, their capacity to provide lateral force decreases. If the tire's friction is entirely consumed by braking, the valuable lateral force becomes zero. At this point, the vehicle will lose traction and slide. Now that we understand the principle of the friction circle, I will explain how this paper leverages load transfer to solve the problem